Lesson 0.4, Solving Quadratics Review. In this lesson, we're going to talk about solving quadratics by factoring and by the quadratic formula. Now, before we jump into things, I want to take a look at two approaches to the same problem. Now, we already solved this equation in the previous lesson. Our answers were 7 and 3. And the method that we took to solve it was by isolation. But as you'll recall, I mentioned that you could have approached this by simplifying and then factoring. But hopefully you can see with a side-by-side comparison that isolation gets you an answer well before factoring is ever going to get you an answer. Notice all I've done on the left side is simplify it to a point that we could actually start the problem by factoring. So how do you know when to isolate versus when to factor? Well, that's easy. It comes down to how many variables do you see? If you only see one variable in the problem versus two variables in the problem, you're going to isolate. One variable means use isolation techniques. In other words, treat it as a linear equation and just solve by the inverse order of operations, starting with getting rid of any addition, subtraction, then multiplication, division, then exponents, then parentheses, using inverse operations along the way. Get rid of addition with subtraction, get rid of a square with a square root, and all that jazz. It's when there are two variables in the problem that you're going to be solving by factoring. One variable solved by isolation, regardless of what degree it is. Two variables you're going to solve by factoring. But keep in mind there are different types of factoring. If it's a binomial, you're going to solve using the GCF method. If it's a trinomial, you're going to solve using the AC method. To help you visualize this process, anytime I ask you to solve a quadratic, the first question is how many variables does it have? One variable means isolate, and that's going to take you directly to a solution. Two variables means factor, but before you can get to a solution, you need to know how many terms there are. If there are two terms, you're going to use the GCF method, which will take you to a solution. If there are three terms, you're going to use the AC method, which actually may or may not take you to a solution, because it's possible that your quadratic is not factorable, which is fine. If it's not factorable, we have more advanced techniques, completing the square, quadratic formula, which will 100% of the time take you to a solution. Now for one of the simplest ideas in mathematics that is obviously true, but it's not true until somebody says it, and which also serves as a foundation to everything else that we talk about basically for the rest of the year as it pertains to solving equations, not just quadratic equations, but any type of equation solving technique, begins with this particular concept. The zero product property says if A times B equals 0, then either A is 0 or B is 0. The only way to multiply two numbers and get 0 as an answer is if one or both of those original numbers were themselves 0. Now this is useful when working with factoring problems. If I want to solve by factoring, first factor it out. X squared plus 2x minus 8 factors into x minus 2x plus 4. Now you can think of this as a product. X minus 2 represents what A would be, and x plus 4 would represent B. So x minus 2 times x plus 4 equals 0. Well, the only way this times that would equal 0 is if x minus 2 itself was 0, or x plus 4 itself was 0, which allows you to break this multivariable equation into two single variable equations. X minus 2 could equal 0, or x plus 4 could equal 0, meaning x is 2 or negative 4. And I know these answers are correct because if I plug them in, 2 squared plus 2 times 2 minus 8 equals 0 is a true statement, which makes that an answer. And if I plug in negative 4 squared, 16 plus 2 times negative 4, 16 minus 8 also equals 0. So that's a correct answer. And the only reason this worked is because to go from this step to this step, we use the zero product property. If this times this equals 0, then each individual factor could itself equal 0. On the other hand, let's say it's not equal to 0, it's equal to 4. Let's factor it just like we did before, and then break it up into two separate statements just like we did before, but instead of it being 0, it's 4. X minus 2 equals 4, x plus 4 equals 4. We get 6 and 0 using basically the same steps. But if I go back to check my answer, starting with plugging in x equals 6, notice I get 6 squared, which is 36, plus 2 times 6, which is 12. So 36 plus 12 minus 8 Well, that's definitely not equal to 4. So I know that 6 is actually not a correct answer. Moving on to x equals 0, plugging in 0, 0 plus 0 minus 8 is also definitely not equal to 4. So neither of those answers are correct because, of course, this entire process is not correct. The only reason I'm allowed to break this quadratic into two linear problems is because of the zero product property. And if it's not equal to 0, then the zero product property does not apply. The fact that I'm multiplying two factors and getting 4 is nothing special. There's no guarantee that either one of those factors themselves is going to equal 4. I can multiply lots of different pairs of numbers and get 4, and neither of them individually themselves being 4. Now, of course, I could do 4 times 1 or 1 times 4, but I could also do 2 times 2. I could do 8 times 1/2. I could do 100 times 1 over 25. So maybe x minus 2 is supposed to equal 100. Maybe x plus 4 is supposed to equal 1 over 25. And that would multiply to give you 4. There's just no guarantees at all. The only way I'm allowed to solve a quadratic by factoring is by first guaranteeing that the quadratic equation is set equal to 0. If it's not set equal to 0, then factoring won't work. So let's solve by factoring. Keep in mind, we know that factoring is the desired choice because there are multiple variables in the problem. There's an x squared and an x, so we know this is a factoring problem. We also have 3 terms, so we know we're going to be factoring by the AC method. But of course, before we do that, check to make sure, is it equal to 0? Yep, it's equal to 0. And also check to make sure, even though we're using the AC method, is there a GCF? If there's a GCF, pull it out. If not, go for the AC method. So feel free to pause here and then play when you're ready. All right, so using the AC method, factors of negative 20 that add to 8 would be 10 and negative 2. So we'll break it up into our double bubble, 4x and 4x, 10 and negative 2. Reduce as necessary, 4x plus 10 equals 2x plus 5. 4x minus 2 becomes 2x minus 1. Now we're done factoring. Since the factors are equal to 0, we can break this into 2 separate equations and solve each one individually. 2x plus 5 equals 0 produces x equals negative 5/2, and then over here we would get x equals 1/2. Now I know you're going to check your answer 100% of the time, so let's go ahead and do that. Negative 5/2, if I plug it back in for x, notice negative 5/2 squared would become 25 over 4, and then if I multiply that by 4, I would get 25. Over here, 8 times negative 5/2, 8 and 2 would cancel out and give you just 4. 4 times negative 5 would be negative 20. 25 minus 20 minus 5 is indeed 0. So I know negative 5/2 is a correct answer. I could also check 1/2 the same way. 1/2 squared is 1/4. 4 times 1/4 is 1, plus 8 times 1/2 would be 4, minus 5 is indeed 0. So I know these are correct. Going forward, I know because you're a good math student, you're going to check your answer every single time, so I'm not going to bother going through it on the video. Here are 3 more examples. Go ahead and pause here, play when you're ready. All right, once again, we have a quadratic trinomial, so factoring by the AC method is going to be preferred. Hopefully you didn't start with 2 times 42 and look for factors of 84 that add to negative 20, because you recognize this problem could be a lot easier if I started with the GCF. Everything is divisible by 2, which means we can factor out a 2. Now also keep in mind, pulling some isolation techniques into this one, I've got that 2 in front, which we can get rid of simply by dividing both sides by 2. So if I just divide this entire side by 2, and then divide the right side by 2, the 2 actually cancels out, and you're just left with this statement. But if you're going to do that, you might as well do it from the very beginning. Skip the GCF step of actually pulling out the GCF, and instead just divide everything by 2. If you recognize that you have a GCF and it's part of an equation, because there are 2 sides to the equation, instead of factoring out the 2 and just leaving it out there to dangle, you could just divide it out. You can't do this on normal factoring problems because there's no other side of an equation to compensate for it. But if it's part of an equation, feel free. So now from here, AC method, factors of 21 that add to negative 10 would be negative 7 and negative 3. We can then factor this into x minus 7, x minus 3, which produces our solutions of 7 and 3. And if you weren't paying attention, this is actually the same problem that we looked at earlier that we never actually finished. So now we know by confirmation that this does indeed actually give you those solutions, 7 and 3. All right, moving on to question C. If you haven't tried this already, pause here, play when you're ready. So of course we can't solve by factoring if it's not equal to 0, and we want it in its standard form of ax squared plus bx plus c. So I'm going to start by distributing the x, and then to make it equal to 0, I'm going to subtract 10 from both sides, giving us 2x squared minus x minus 10 equals 0, and now we can start the problem. Factors of negative 20 that add to negative 1 would be negative 5 and positive 4. So I can break this into 2x minus 5 and 2x plus 4, which reduces to 2x minus 5, x plus 2. If you break it up and solve, you're going to get 5 halves for the first factor and negative 2 for the second factor. And lastly, again, pause here, play when you're ready if you haven't already. 3x squared minus 16 equals negative 22x. Let's get it equal to 0 by moving the 22x over. It becomes a positive when you do that. I do not see a GCF, so we'll go ahead and do 3 times 16. Keep in mind, 3 times 16 is really 3 times 10 and 3 times 6. So 3 times 10 is 30, 3 times 6 is 18, 30 and 18 would be 48. So negative 48, factors of negative 48 that add to 22. That would be 24 and negative 2. So we'll break this up and reduce. And then my two solutions will be 2/3 and negative 8. But of course, factoring doesn't always work. You need to make sure that you have other techniques in your back pocket just in case. If you refer back to the flowchart, in situations that are not factorable, we can use either completing the square or the quadratic formula. Now, completing the square is a technique that you talked about last year in Algebra 2. It's going to come up a lot later on in this course, but when it comes to solving quadratics, if something's not factorable, I'm just going to go straight to quadratic formula. So let's do that. Given a quadratic function of the form ax squared plus bx plus c equals 0. Notice once again, it has to be equal to 0 in order for this formula to work. The solutions are negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't have that memorized now, stop the video here and then take this course in a later year because you haven't been paying attention for the last 2 years of algebra. Now, for those of you who are interested, which I hope is 100% of the people taking a pre-calculus course, I'm going to take a few minutes here to go through the derivation of the quadratic formula, just so that you have a little background and you know where it's coming from and why it works. If you're not interested in the derivation, that's fine. I do think less of you, but I don't know that you're skipping ahead. Feel free to go ahead and skip ahead to the examples for this, but if you are interested, I encourage you to take a couple of minutes and pay attention to this next little piece. Perfect squares. Again, we've talked about this a couple of times so far. We know that if I square a binomial x plus b, I'm going to get the perfect square trinomial x squared plus 2bx plus b squared. Now, I mentioned a few minutes ago about the process of completing the square. So a quick review of completing the square has to do with starting with this trinomial. We know that the relationship between this guy and its factored form is that whatever I have right here, this 2b, if I cut that in half, I get 1b, or just b. If I square it, it gets me to this piece right here, and then the b value itself is what goes in the factor over here. So if a trinomial is a perfect square, I should be able to take the 2b value right here, cut it in half, and square it to go right here, and then that b value itself is part of the factor over here. Now, of course, this only works if x squared has a coefficient of 1. If it's anything other than that, we'd use techniques that we talked about in previous lessons. So, for example, x squared plus 6x, if I asked you to complete the square, we'll take the number in front of x, which represents 2b, or 6, cut that in half, which would be 3, and then whatever that number is right there, we would square it to complete the square. And then we know, because half of 6 was 3, we know that this factors into x plus 3 squared. Again, cut the b value in half and square it, we get 9, and then that becomes its factorization, x plus 3 squared. If I complete the square on x squared minus 10x, half of negative 10 would be negative 5, squared would be 25, which means this factors into x minus 5 squared. Half of 7 would be 7 over 2, square it, that would be 49 over 4, completing the square, and then we could factor it into x plus 7 over 2 squared. For more practice with completing the square, I'd encourage you to do a Google search of completing the square. Now, how does that apply to the quadratic formula? Well, consider the original equation that we started with was ax squared plus bx plus c equals 0. Anything of this form can be solved using the quadratic formula. Now, to derive the quadratic formula, I'm going to start by completing the square. Now, when I'm completing the square, typically this piece is left open. So let's go ahead and get rid of that plus c by subtracting it to the other side. So now I've got some room to complete the square. I also don't want to complete the square when there's a coefficient in front of the x squared. Another quick, easy fix, let's just divide everything by a, which allows me to have x squared with a 1 as my coefficient, and then b becomes b over a, and c becomes c over a. I now have an equation that's ready to be completed by completing the square. In order to complete the square, we're going to take whatever this says right here, and we're going to cut it in half. Half of b over a, well, again, you can think of that as b over a times 1/2 would be b over 2a. So half of b over a squared would be b over 2a squared. Now keep in mind, because we're solving an equation here, whatever I add to one side, I have to add to the other side. So I've added that b over 2a squared to both sides. Now that on the left side I've completed the square, I can factor it as a perfect square. Not knowing what a and b actually are is not relevant, because if it's a perfect square, it automatically factors into x plus whatever half of b over a was, or b over 2a. So now we're going to leave the left side of the equation alone for a little while, and let's simplify the right side of the equation. Starting with this b over 2a squared, I'm going to clean that up into b squared over 2a squared, or 4a squared. I'm adding fractions, so we need a common denominator. So if I multiply top and bottom of this fraction by 4a, that would give me 4ac on the top and 4a squared on the bottom. I can then rewrite this as one big fraction, and I'm going to go ahead and switch the order to have the leading term be a positive, so it becomes b squared minus 4ac. At this point, I would understand that you're starting to get a little bit excited because you're starting to see the quadratic formula kind of appear out of nowhere. So let's go back to the left side. Let's get x by itself. In order to get x by itself, we'll use those solving techniques. I only have one variable there, so I'm going to isolate, getting rid of the square first by square rooting. If I square root both sides, that gives me x plus b over 2a on the left equal to plus or minus. Anytime you take a square root, you put a plus or minus, b squared minus 4ac all over 4a squared. Square rooting a fraction really means square rooting the top and bottom separately. So the top looks ugly, so I'm going to leave it alone. On the bottom, though, 4a squared is itself a perfect square. The square root of 4a squared is, of course, 2a. And oh my gosh, one more step. If we subtract b over 2a from both sides, we have what almost appears as the quadratic formula. We'll go ahead and rewrite that as a single fraction since we already have a common denominator, and look at that. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Regardless of what the a, the b, and the c value are, if I have an equation written of the form ax squared plus bx plus c equal to 0, I can get the solution x by following the formula negative b plus or minus square root of b squared minus 4ac all over 2a. So let's practice. 2x squared plus 5x minus 4 equals 0. Pause here, play when you're ready. Okay, so hopefully you started by attempting to factor. You should always attempt to factor before jumping into quadratic formula. If something is factorable, it will always be quicker to factor it than to go through the quadratic formula. So if I try to factor and find factors of negative 8 that add to 5, I'm stuck. I can't think of any factors that multiply to negative 8 and add to 5, which means this is not factorable. And if it's not factorable, I'll go straight to the quadratic formula. So negative b would make it negative 5 plus or minus the square root of b squared minus 4ac all over 2a. I'm going to start simplifying underneath the radical. 5 squared is, of course, 25. And then I'm going to go with negative 4, and negative 4 gives me positive 16, and we still have the times 2. So 16 times 2 is 32. Add that to 25, we get 57. Now, 57 is a prime number. It's not a perfect square, so I can't take a square root, and there's no perfect squares that can be factored out of 57, which means we're done. -5 plus or minus the square root of 57 over 4 is my final answer. Now, a little hint is that if this was factorable, then that would have been a perfect square. If you see a perfect square underneath the radical, then you could have factored it. And of course, if you see a perfect square underneath the radical, that means that you're not done. You have to keep going. So when it's not factorable, it's always going to be quick and easy like this one. But when it was factorable, the quadratic formula is going to take at least 3 to 4 more steps to get to the final answer. And by that time, someone who was factoring it would have already been done. So if you see a perfect square underneath a radical, hey, guess what? You picked the harder method to do this, but you might as well keep going because you're already halfway there. All right, here are 3 more examples. Give these a try, pause here, play when you're ready. All right, 6x squared minus x plus 5 equals 0. Start by the AC method, factors of 30 that add to -1. There aren't any, so quadratic formula. 1 plus or minus the square root of b squared minus 4ac all over 2a. Please be super careful on that b squared. The b value is -1. -1 is being squared. It should not say -1 squared. It should say -1 squared, because -1 squared is actually 1, versus the way it's written here, it's actually -1, because -1 squared literally means -1 times 1, because only the 1 itself is being squared. If I want to square the negative, I need to put it in parentheses. Since the b value is indeed negative, I need to put it in parentheses. So carrying on, underneath the radical, that's going to give me 1 minus 4 times 6 times 5 would be 4 times 30, or 120. 1 minus 120 is -119. Keep in mind, 119, once again, is not a perfect square, so we know that we chose properly with doing the quadratic formula and not factoring. But also keep in mind, there's a negative there, and anytime I see a negative, I need to pull it out as an imaginary number. We can't forget the old stuff just because we're moving on to new stuff. Nothing else can be factored out of that 119, so final answer. 2x minus 1 minus x squared equals 4. Again, if you haven't tried this already, pause here, play when you're ready. So with this one, we're all out of order. We can't solve this in its current form, whether by using the quadratic formula or by factoring, until it's in the appropriate order. So if I reorder everything and move everything to one side, we should get x squared minus 2x plus 5. Factors of 5 that add to -2, thinking about it, there aren't any. So this one's not factorable. We'll go to the quadratic formula. Simplifying the inside, we're going to get 4 minus 20, or -16. Now you might think to yourself, well, wait a second, isn't 16 a perfect square? It sure is. And that doesn't say 16, it says -16. So we're okay. This was not factorable because -16 is not a perfect square. But a negative is imaginary. So square root of a negative is imaginary. Square root of 16 is 4. So this becomes 2 plus or minus 4i over 2. Simplifying one more step, divide both 2 and 4 by 2. You're going to get 1 plus or minus 2i. Final answer. All right, and one last problem for the day. Now on this one, hopefully you recognize this as not needing the quadratic formula. You can solve this by isolation, you can solve this by factoring, but I also want to point out the quadratic formula will still work. And just for kicks, let's use the quadratic formula. Keep in mind though, the b value is missing, therefore it's 0. Just because the term is 0 doesn't break the formula, it will still work. 0 plus or minus the square root of 0 squared minus 4 times -9 all over 2 times 4. Cleaning up the inside, that's going to be 144. We'll go ahead and stop writing the 0 on the outside because it's 0 and it's not needed. So we have plus or minus the square root of 144 over 8, which is plus or minus 12 over 8, which is 3/2 and -3/2. Notice, if we had solved this by factoring, we're going to get the same answer. 4x squared minus 9 is a difference of squares. 2x minus 3, 2x plus 3, which again produces 3/2 and -3/2. Now, of course, on this one, factoring was way quicker than the quadratic formula, as well as a lot less writing. It's easier to solve this one by factoring simply because you connect pencil to paper a lot less. But even factoring, I think, was overkill because there's only one variable here. You could solve it by isolating. add 9, divide by 4, and then take your square root, you get plus or minus 3/2. 3 different ways to solve the same problem, but all of them give you the same answer. Your goal for any random problem that you're working on is to identify what the most appropriate method is based on the structure of the original problem. So good luck.